I shared this graph with you back in August, and to refresh your memory, it's summarizing the results of some pairwise comparisons of changes in size of Lampsilis siliquoidea between summer and fall in 4 different years. So, summer to fall of 2017 and summer to fall of 2018, summer to fall 2019, and we skipped 2020, and summer to fall of 2021. And what this means is that we saw a increase in size between summer and fall of a little over 1 cubic centimeter in 2017. We saw a decrease in size of about 1/4 of a cubic centimeter in 2018, increase in size of almost 4 cubic centimeters in 2019, and then between summer and fall of 2021, again we saw a decrease in size of about 3/4 of a cubic centimeter. And statistically speaking, this value of 3.72 was significantly greater than the value that we saw in 2018, and also significantly greater of the value in 2021. After seeing that, one of you intrepid viewers sent me an email asking about the possibility of observer error in these data. And that's an excellent question, and one that's occurred to me from time to time. So I've decided to explore that a little bit and see where it leads. And as with many questions that deal with variation and uncertainty and those kinds of topics, I like to turn to my small collection of statistics books. And it's really kind of remarkable how many pages of any one of these texts or other texts on statistics are devoted to analysis of data, and just how few pages are given over to the practical issues involved in actually collecting the numbers. And I'll give you a little sample of what I found. The first book is by this guy named Lyman Ott. What a great name. Published in 1984, and this was the first statistics book that I ever read. And both my wife Ellen and I have copies of Ott. No coincidence, because this is the class in which she and I met long ago. And she was in her nursing program, or Masters of Psych Mental Health Nursing, and I was working on a master's degree in biology at University of Nebraska, Omaha. Anyway, what's in Ott? Very little on the topic of outliers and inter-reader reliability, that sort of thing. The only thing I could find here recently that touched on this matter was this quote from the section on box plots. Basically, it just recognizes that outliers exist, and that's it. Another text that I consulted called Simplified Statistical Analysis, it really has a lot of practical value, and there was a section on variation, but mostly what it went into was comparing and contrasting biases, comparative and psychological bias that occurs during collection of data in an experiment. The 6th edition of Statistical Methods gives a mathematical method of how you go about throwing out unusually large or small measurements, so outliers. But of the 4 books, the best discussion that relates to the topic at hand comes from Czar. and I love this quote. Human error may exist in the recording of data. For example, a person may miscount the number of birds in a tract of land or misread the numbers on a heart rate monitor. He even goes on to say, or a person might obtain correct data but record them in such a way, perhaps with poor handwriting, that a subsequent data analyst makes an error in reading them. This one really makes me chuckle. We shall assume that such errors have not occurred. but there are other aspects of accuracy that should be considered. And at least I'll give Czar the credit that he acknowledges that humans aren't perfect. And this is a little bit like, the preacher getting up on Sunday morning and saying, humans should be good. Well, we know they're not, and we screw up. But a lot of times, I think in statistics and in science in general, we forget that scientists are humans, and we do in fact make mistakes. Well, what are you going to do about that? Try to do better. But that isn't really what we're looking at here, and Czar goes on to give us some ideas of what to do next. So he gives a nice example. Basically, he presents a data set that's supposedly some weights of mallard ducks in kilograms, and he just kind of lists them out. And at first glance, you're like, okay, well, here's a bunch of numbers. But the longer you stare at it, it's like, there's problems here. This is kind of a hot mess. And the first one that jumps out is this rather large value here. Even if you're a little fuzzy on your metric system, you see values in the 3 to 4 range here. Yeah. And then you get toward the end, it's like, oh my goodness, that's a big duck. That duck is like 10 times the size of all the other ducks. And what Czar suggests is, well, perhaps the person who recorded these data just slipped the decimal point. So maybe this 39.8 should really be 3.98. And so maybe you go back and you talk to the person that did this and like, yeah, I slipped a decimal point. Okay, well, we'd be justified in making that adjustment in the raw data. So we can, without too much hesitation, change that decimal point, put it in back in the data set where it belongs, and that looks pretty reasonable. Yeah. And we have justification for that because we talked to the person who did it. They admitted their sin. We gave them absolution. All is good. Okay, well, let's deal with this other one here that's like more than twice as big as the others. That's a really big duck. And there's 2.2 pounds in a kilogram. So I wonder, did Sally mess that up? So we go back, we talk to Sally, and she's like, I had the scale set to read in pounds rather than kilograms. Oh, okay, all right. So we do that conversion, and that lets us get a value that's a lot more reasonable. Sally admitted her mistake. We can we can fix this. Yeah, we can fix this. So things are looking a lot better, right? We have one other outlier at the other end of the spectrum, this 1.87 value here. And this time it doesn't seem to be a mathematical error. It's an error in species identification. So when we go back and we look at all of our ducks again, we see that, my goodness, this 1.87 value came from that duck, which is not a mallard. So we measured the wrong duck, or our research assistants did. Somebody messed up. We're looking at mallards, not anything else. So that allows us to go in and just completely strike out this first value. So this variation that we're seeing here in these numbers is the sort of stuff, some of it anyway, that's due to genetic variation. So it's the variation that allows evolution to occur, for natural selection can act upon natural variation that we see in plants and animals, in this case ducks. And it's partly due to that, that value that biologists place on naturally occurring variation that Czar makes this statement. You know, having gone through these exercises in quality control, you might say, Czar says, you know, once you've done that, it's not okay to just throw out inconvenient data because it doesn't conform to your notions. So you have to leave it in. As you know, when we measure mussels, we measure 3 different linear aspects of their size. We do the length, we do the height, and we do the width. So when we're looking at this mussel from the side, the red line is the shell length, and then the perpendicular blue line to that red line is the shell height. That appears to be straightforward and pretty easy to do, you know, on a picture, but with an actual shell in your hand and the calipers in the other hand, it turns out that it's not quite that easy. A lot depends upon where the researcher places the jaws of the calipers, and if you look at these next couple pictures, you'll see what I mean. You could put that blue line, that shell height measurement, in several different places on this sort of curvy shape. So you might go a little bit farther toward the front of the shell, or you might place it just a little bit farther aft. And really the point of this whole video, and at least one more that'll be subsequent to it, is we know what the protocol is. It's really simple. The question is, how well do we fallible humans implement it? Fortunately, I'm not the first person to go down this road. There was a study done back in the early 90s by Downing and Downing on a couple of populations of freshwater mussels in a lake up in Minnesota. And it just so happens that the 2 species that they studied were the same species as we have here in Indiana in Crooked Lake. Lampsilis siliquoidea was one of them, and what we now call Pyganodon grandis was the other. And these folks measured shell height. They did not do length or width. They only focused their efforts on shell height. And they found over a period of years from 1986 to 91, so what's that, 5 years, over 5 years, some of those mussels actually decreased in shell height. So looks like around 12 or so got smaller. They shrank. Their shell height decreased by, looks like, 2 millimeters. 6 or so decreased by 3 millimeters. Some of them decreased even more than that, like more than 5 millimeters decrease in shell height over a period of 5 years. And this was the first time that I'm aware of, anyway, that researchers found any mollusk, hard-shelled mollusk, actually decreasing in size. So it's kind of a big deal. And this assertion that mollusk shells can actually shrink was so radical that they needed to demonstrate that the shrinkage was greater than could be accounted for by measurement error. So they actually measured how much measurement error occurred. And they used a nice simple method for determining approximately how much measurement error normally occurs when people do repeated measures of museum specimens. And that's the part of Downing and Downing study that I want to focus on in this video, because that's the method that I intend to use with our mussels here in Indiana. The caption on that figure that I just showed you gives a really nice summation of their simple statistical method that they used. And basically they took and remeasured 10 Lampsilis siliquoidea shells and 10 Antodonta, or what we now call Pyganodon shells. And they had the same person measure those 20 museum specimens 30 times. Now, they did them in random order each time. I don't know. I suspect they did it on different days. They might have done them all at once. I can't imagine having having the patience to do that all in one sitting. But anyway, what they wound up with was 20 times 30, which is 600 individual measurements. And if that next sentence is a little bit hard to follow, don't worry. I'm going to go through an explanation for you, an example, both to clarify it to you and to remind me just how did they do this? Now, the Downings did not present their raw data, and that's okay. For the purposes of demonstration, what I've done is gone through and made up some data. So these are not real data, but they're intended to be a basis upon which we can discuss this further. And so I just kind of used Excel and came up with a data matrix to look something like what Downing and Downing probably worked with. And to kind of orient you here, what I have is 2 sections, one for the Lampsilis and one for what they called Antodonta, so Pyganodon. And for each of these 2 species, or genera, we have individual mussels. So you might say Lampsilis siliquoidea number 1, number 2, number 3, and so forth on up to number 10. So we have 10 Lampsilis, and then we have Antodonta number 1, Antodonta number 2, and so on. And so all the measurements for this Antodonta number 3, the individual measurements, appear in this column here, right? So each column is measurements from a particular mussel shell. And this is all in Excel, so it's really easy to get things like averages and so on. And down here at the bottom, I have the mean values for each of these columns. So this 73.17 is the mean or the average for all of these 30 measurements in the column above it. So the mean value for Lampsilis number 2 is 80.59 and so forth. Now this next little step is exquisitely simple. Basically, you take this mean value, the average of 73.17, and subtract from it one of these individual measurements. So 72.24 in this case. And we're going to use that method to create another table that's going to look very similar to the first, only this next table is going to be the remeasurement errors. So each of these values is going to be the result of subtracting the individual measurement from the mean value. So as promised, here's that massive list of 600 values that are remeasurement differences between the individual measurement and that of the average. Now what we're going to do next is take all of these 600 numbers and put them in one big column, and then we're going to sort them from top to bottom. And of course that column is going to be enormously huge. So I've shortened it a little bit here. Take that column, sort it from big to little, and what we wind up with is a column of 600 numbers that have the big ones at the top up here, and the little ones at the bottom, and all the others in between. And that ranges, in this case, from 1.28 down to negative 1.13. Now, in order to make this fit onto the page, I've eliminated some in the middle. So in the actual real Excel spreadsheet, there's a number 18, a number 19, a number 20, and so on up to 577. And I've taken those out. I've hidden those from view on this one. So there's a whole lot of numbers that should go where this arrow is. And so here we have this list, right, where the measurement differences are sorted from big to little, and they're ranked. So each one has a number associated with it from 1 to 600. And what I want to do, what Downing and Downing did, what I want to do too, is find out what that middle portion ranges from and to. So to find that out, I'm going to take the total number of numbers, so I have 600 in my list, 600 ranks, and multiply it times 0.95 to get that middle 95%, and that gives me 570. So what I know is that there's 570 here in this middle part. Doesn't look like it, but that's because I took some out for the purposes of the video. So 570 belong in the middle. All right, well, so if 570 belong in the middle, then how many should go on either end up here, right? Up here and down here? So if we take 600 minus 570, that leaves us 30 that ain't in the middle. Take 30, divide it by 2, and that tells us that 15 go up here, and 15 belong down here. That knowledge allows me to draw these lines here. So there's a line between number 15 and number 16. And there's another line here between the bottom 15, which is 586, and the last one in the middle portion, so 585. So those two lines let me determine the limits of this 95% range. So you might have been staring at this over here the whole time I've been going through this explanation. So the answer to my little problem here is that the 95% range of measurement errors in this example runs between negative 0.92 and positive 0.96. All right, so that gets us part of the way there. At least that outlines the method that I intend to use for looking at Lampsilis siliquoidea here in Indiana with our people. So I'm going to modify Downing and Downing's methods a little bit to suit what we're doing. But anyway, you have the basis, the mathematical basis for how I intend to go about that, and we'll pick that up in the next episode. So thanks for watching. See you then. Bye.